The general equation here is that V output is given by that A differential times V differential plus A common mode times V common mode. Let's calculate for the first case. V output 1. The differential component is 2 microvolt. The common mode component is the average of these two guys, which is 100 microvolts. So we end up with V output 1 here, about 30 millivolts. If we repeat the equation here, well, that common mode component is going to disappear. There is no common mode component here for this second case. So it's going to be 0. So surprisingly, one of the outputs here is a 30 millivolt, and the other output is 20 millivolt, although the differential input voltage is the same. What happened? What happened is that there is something called a common mode component. And we cannot ignore the common mode component. The common mode component is a figure of merit of amplifiers. What is a figure of merit? What do you mean by a figure of merit? Figure of merit means a quantity, it's an electrical quantity by which we rate the performance of a component or a system or a circuit. That's the common mode. That's and the ratio between the differential component and the common mode component is called the common mode rejection ratio. Common mode rejection ratio. So that's called the figure of merit, you know. Examples of a figure of merit. It's like the grades, student grades, A, B, C, D, whatever. These are figures of merit. It is a figure of merit. It's an evaluation criteria. So, yes, you could have totally different answers just because the common mode component plays a bigger role in one case than the other case. The quotient is the common mode rejection ratio, and you're going to have a better amplifier if this common mode rejection ratio is high. So typically, I would say for single stage amplifiers, if this ratio is 20 or 30 decibels, well, that's kind of a typical, you know, for a single stage amplifier. For a two-stage amplifier, you can probably reach 60, 70 decibels. For a three-stage amplifier, you could probably reach 100 or 120 decibels. The common mode rejection ratio. I remember building an instrumentation amplifier myself long ago, and it had a common mode rejection ratio of 117 decibels, but it incorporated 3 op amps. But if you have a single op amp in a circuit, you won't get that high common mode rejection ratio. You're probably gonna get 30, 40 decibel common mode rejection ratio. Let me analyze now the differential amplifier. We need to compute the differential gain and the common mode gain of a differential amplifier. That's what we're going to start doing here. Well, here's a differential amplifier. Generally, these two voltages are going to be out of phase. I'm talking about the AC voltages, of course. but as far as the DC voltages are the same at this point at both outputs. The difference in DC between the two outputs is called an offset voltage. When it's DC, it's called offset. But the two ACs generally are having opposite phase. There is 180 degrees phase shift between these two waveforms, and I am asking the 430 people, 430 lab students to build this and see this on the oscilloscope. You need to see this on the oscilloscope to understand. By the way, the experimental part is essential for complete understanding. Don't ever think that you can understand electronics without building anything in the lab. You must build things in the lab so that you understand electronics. There are two equations here describing the two outputs. There is a minus sign difference here. The two common mode components at the output are the same. And the differential components are opposite because they are out of phase. But the common mode component is the same. So equation 1 and 2 describes the situation very well. When we want to characterize an amplifier, we need to determine the two components. We need to determine A sub D and we need to determine A sub C. So let's now start determining AD and AC. Let's now start by AD. All right, so we need to find the value AD, the differential gain. So in this case, we need to make the common mode component equal to 0. Look at this equation. Let's assume you are in the lab and you measured both outputs, output 1 and output 2. And what's the best way to determine AD? Simply make VC equal to 0. Make the common mode component equal to 0, meaning that the two inputs, the average of the two inputs is 0. The DC, the average, not the DC, the average of the two inputs is 0. That makes the common mode component equal to 0. So this way you will end up with one equation and one unknown. You know VO1 and you know VD, so you will be able to determine AD. So we have two equations and two unknowns. We are going to solve them by creating two circuits to simplify the situation. And then when we build the two circuits, we're going to simplify things as follows. Our goal here is to determine AD, the differential gain. All right, so let's make VC equal to 0. The common mode component equal to 0. So how are we going to do that? We're going to apply VD over 2 here. We're going to apply minus VD over 2 here. So we took care of this first part. All right. So we have a circuit with two equal and opposite inputs. That must be a special circuit. We need to simplify it. How do you simplify it? We're gonna do something called longitudinal bisection. This way, longitudinal bisection. So the circuit has symmetry because you're applying VD by 2 here, you're applying minus VD by 2 here. All right. As a result of applying two equal and opposite inputs, you're going to have two equal and opposite currents here. If this current is IE, this current is going to be minus IE because you have two equal and opposite inputs. You're going to have two equal and opposite currents. That will result in a zero AC current going in this tail resistor. No current's going to go this way. No AC current, I should say. The DC current is there, but there will be no AC current going this way. When you do that, the problem boils down to two common emitter transistor amplifiers. So when you consider this current to be zero, this is going to be shorted here. You're going to end up with this is half of the circuit, and this is the other half of the circuit. As a result of bisection, you end up with this. Well, it is sufficient to analyze only one half because due to symmetry, the other half will give equal and opposite results. So we can take one half of the circuit only and analyze it. It boils down. It becomes like a common emitter amplifier here. Look at that. See? Minus VD by 2 divided by RC. So you're going to get V output 1 divided by VD equal to that. That's called the differential gain, which is minus GM RC over 2. That's called the differential gain. All right. Similarly, we